This is Lesson 12 in our Calculus 1 series, the chain rule. In the last couple of lessons, we learned some basic differentiation formulas, and we learned how to take the derivative of a product or quotient of functions. In this lesson, we learned how to differentiate a composition of functions. So that's when you have one function plugged inside another. So the chain rule says that the derivative of f of g of x is equal to f prime of g of x times g prime of x. So we're taking the derivative of the composition here. We have g of x plugged inside of f. And so the first thing we do is take the derivative of the outside function, f prime, and evaluate that at g, at the inside function, and then multiply by the derivative of the inside function. Now we could use a different notation for this. If we let y equal f of u and u equal g of x, we can write the chain rule as dy dx is equal to dy du times du dx. So again, dy dx is the derivative of the composition taken with respect to x. F prime, evaluated at u, at g of x, is written as dy du. And then g prime of x is written as du dx. So this is just another notation for the chain rule. So let's take a look at an example. Here we have y equals x squared plus 3 to the 5th power. And so we notice that our outside function is going to be u to the 5th power. So f of u is equal to u to the 5th. And our inside function is going to be x squared plus 3. And so here we have f of g of x with this notation. And so the chain rule says that y prime is going to be f prime of g of x times g prime of x. So let's take f prime of u, that's going to be 5u to the 4th, and g prime of x is going to be 2x. So here we want to take g and plug it into f prime. We want to take g and plug it into f prime. So that's going to be 5 times x squared plus 3 to the 4th. And multiply that by g prime of x, which is 2x. And then simplifying, let's just combine our 2x and our 5 in the front, and that's 10x times x squared plus 3 to the 4th power. Now it's not going to be necessary to write down the outside function and the inside function and their derivatives like this. We can do it a little bit more intuitively by looking at our original function. Remember that if this was just an x in here, if this was just x to the 5th, you would say the derivative is 5x to the 4th. So we're going to start there. We're going to take the 5 down and subtract 1 from the power. That gives us 5 times x squared plus 3 to the 4th power. But because this is not just an x, it's a function of x, we have to remember to multiply by its derivative, 2x, and then simplify. And so usually we're not going to write all of this down. We're just going to look at the function, take the derivative of the outside function, and then multiply by the derivative of the inside function. So again, here, that would be taking the 5 down in front and having 5 times x squared plus 3 to the 4th power. We start there. And we realize because this is not just x, it's a function of x, we have to multiply by its derivative. That's what the chain rule says. And so that's multiplied by 2x, and then we simplify. So for this type of composition, in general, that looks like y equals g of x to the nth power. The n comes down, we have g of x to the n minus 1, and we multiply it by g prime of x. And this is combining the power rule and the chain rule. So here if we have y equals radical x squared plus 2x, we know that this is equal to x squared plus 2x to the 1/2 power. So let's write it as x squared plus 2x to the 1/2 power. Now let's use the chain rule on this. The 1/2 is going to come down in front. We're going to have 1/2 x squared plus 2x to the negative 1/2 power. We're subtracting 1 from this exponent. So we have negative 1/2 here. And again, because this is not just an x, it's a function of x, we have to take its derivative. That's what the chain rule says. So we're going to have 2x plus 2 here. And now we just want to simplify. Notice we have a negative exponent here, so we want to bring this x squared plus 2x down into the denominator to the positive 1/2 power, or under a radical. And notice the 1/2 and the 2x plus 2, we can cancel a factor of 2. So we're just left with x plus 1 in the numerator. And that's our derivative. Let's take a look at another. Here we have the cube root of sine x plus 2. Before we use our derivative rules, we want to rewrite this cube root as a 1/3 power. So let's write this as sine x plus 2 all to the 1/3 power. Now, to take the derivative, the 1/3 comes down in front, and we subtract 1 from the exponent. So we have 1/3 sine x plus 2 to the negative 2/3. And again, by the chain rule, because this is not x, it's a function of x, we have to take its derivative and multiply that. And so that's cosine x here. And again, we want to simplify by writing this without any negative exponents. So this sine x plus 2 to the negative 2/3 is going to go down to the denominator as a positive 2/3 power. We already have this 3 in the denominator, so the sine x plus 2 to the 2/3 will join the 3 in the denominator. And we have cosine x in the numerator. And that is our derivative. Let's take a look at another. Here we have y equals sine x plus cosine x all to the 6th power. Please pause the video, use the chain rule to find y prime. Using the chain rule, the 6 comes down in front and we subtract 1 from the power, so we start with a 6 sine x plus cosine x to the 5th power. And then by the chain rule, because this is not x, it's a function of x, we have to multiply by its derivative. So that's going to be cosine x minus sine x. And that is our y prime. Let's take a look at another. Here we have y equals x squared plus sine square x. Now this notation, sine square x, can be a little bit confusing. We have to remember that this is just shorthand notation for sine x quantity squared. So whenever you're taking the derivative of a sine square x or a cosine square x, I encourage you to rewrite it with parentheses to make it more obvious how that composition works. So here I'm rewriting my function as x squared plus sine x quantity squared. Now I'm ready to take the derivative. Y prime is going to be 2x, and on this term I need to use the chain rule. So I have plus, the 2 comes down in front, I have 2 sine x to the 1st power, multiplied by the derivative of sine x, and that's cosine x. So I have 2x plus 2 sine x cosine x. And that is our y prime. Let's take a look at another. Here we have y equals cosine of pi x. So now notice we have pi x plugged inside the cosine function. So this is a different type of application of the chain rule. Remember, the chain rule says take the derivative of the outside function and evaluate at the inside function. Well, what's the derivative of cosine of something? It's going to be negative sine of that something. So we're going to start with negative sine of pi x. But because this inside function is not just x, it's a function of x, we have to multiply by its derivative. And that derivative is pi. So we have a negative sine pi x multiplied by pi. And just to simplify, we'll bring this factor of pi out in front with the negative, and we have negative pi sine pi x. And that is our y prime. So again, we have a composition of functions here. We have pi x plugged inside the cosine. And the chain rule says, start by taking the derivative of the outside function. The outside function here is, say, cosine of u. Well, what's the derivative of cosine u? It's negative sine u. So negative sine u multiplied by the derivative of u, the derivative of that inside function. And so we're here. Let's take a look at another. Here we have 2t over radical t squared minus 9. So the first thing we notice is that we have a quotient of functions, which should tell us that we should be starting with the quotient rule. But within that quotient, we notice that we have a composition of functions. We have t squared minus 9 to the 1/2 power in our quotient. So we have a composition in a quotient. That means we're going to need to use the chain rule within the quotient rule. And we're going to want to start then with the quotient rule. So what does the quotient rule say? It says y prime here is going to be the bottom times derivative of the top minus top times derivative of the bottom over bottom squared. So the derivative of 2t is equal to 2. And for the derivative here of t squared minus 9 to the 1/2, we're going to need to use the chain rule. And so that derivative is going to be 1/2 t squared minus 9 to the negative 1/2 multiplied by the derivative of t squared minus 9, which is 2t. Now at this point we need to simplify. Well, the first thing I notice is that we have a 2 here and a 1/2, so I'm going to cancel those. But also notice that we have a negative exponent only in one term of the numerator. So I don't want to make a fraction in one term of my numerator of another fraction. Instead of creating a fraction within a fraction, let's simplify it by multiplying the numerator and the denominator here by t squared minus 9 to the positive 1/2 power. So for this term on the right, that'll cancel to a 1 and we'll be left with 2t squared. And of course, don't forget we have to distribute this as well to the term on the left. But that's nice as well because then we have a 1/2 power here and a 1/2 power here. So we get t squared minus 9 to the first power multiplied by 2. So we have 2 times t squared minus 9 minus, we have a 2t squared here that's left, a 2t squared. And then multiplying the denominators, we have t squared minus 9 to the 3/2 power. So we're here. And we're almost done. We notice that we can simplify a little bit more in the numerator. This is 2t squared minus 18 minus 2t squared. So the 2t squares will cancel and we'll be left with a negative 18 over t squared minus 9 to the 3/2 power. And that's our derivative here. Again, remember with this problem, we noticed that we had a composition within a quotient. So that means we use the chain rule within the quotient rule. So you start here with a quotient rule. Let's take a look at this problem. Here we have the product of two compositions. We have t plus 1 to the 2/3 power multiplied by 2t squared minus 1 to the 3rd. So we have compositions within a product. We start with the product rule. Within the product rule, we're going to have to use the chain rule. The product rule says take the derivative of the first, multiply by the second, plus the first times the derivative of the second. So here, we're going to use a chain rule to take this derivative, and that result is here. And here, we're going to use another chain rule, and that result is here. So let's take a closer look at that. Here, the 2/3 comes down in front, and we subtract 1 from the power, so we have 2/3 times t plus 1 to the negative 1/3 power, and then we have to multiply by the derivative of the inside function here, so that's just a 1. For this derivative, the 3 comes down, and we have 2t squared minus 1 to the 2nd power, and then we have to multiply by the derivative of the inside function, so that in this case is 4t. So we're here. And there isn't very much we can do here to simplify, but there are a couple of things. Let's take this t plus 1 to the negative 1/3 and bring it down to the denominator, writing that to a positive exponent. So we'll bring it down to join the 3 in the denominator. So we're going to have left in the numerator 2 times 2t squared minus 1 to the 3rd. And in the denominator, we'll have 3 times t plus 1 to the positive 1/3 power. And here, let's just combine our 3 times 4t and bring it out front of that term. So we have 12t times t plus 1 to the 2/3 times 2t squared minus 1 squared. And we can leave it here. Now let's take a look at this composition. We have cosine to the 4th of sine to the 3rd of pi x. So we have a whole chain of compositions here. The first thing I want to do, as I mentioned earlier, is get rid of this shorthand notation with cosine to the 4th and sine to the 3rd. So cosine to the 4th is just shorthand notation for cosine of all of that to the 4th power. So I bring that 4th power outside some parentheses. Now I want to do the same thing with this sine to the 3rd. This is sine of pi x to the 3rd power. So what we have here is pi x plugged into the sine function, all of that taken to the 3rd power, all of that plugged inside the cosine function, and then all of that taken to the 4th power. So we have a series of compositions here. So we're just going to start with the outermost composition and work our way in. So we have a function of x to the 4th power. The chain rule says to take the derivative, bring that 4 down, and take all of that to the 3rd power. 4 times cosine of sine pi x to the 3rd, all of that to the 3rd power. And then multiply by the derivative of the inside function. So we're here. Okay, now to take this derivative, we're going to have to use the chain rule again. This derivative is here. Here we have cosine of a function of x. So its derivative is going to be negative sine of that function multiplied by the derivative of that function. So we're here. Now to take this derivative, we're again going to have to use the chain rule. This derivative is here. Here we have sine pi x taken to the 3rd power. So we have a function to the 3rd power. So the 3 comes down in front, and we have sine pi x to the 2nd power multiplied by the derivative of sine pi x. Now to take this derivative, we're again going to have to use the chain rule. Here we have sine of pi x, and so the derivative is going to be cosine of pi x multiplied by the derivative of pi x. The derivative of pi x is just pi, and so now we're through. Let's put everything together. Let's take this factor of pi with this 3 and this negative 1 and this 4, and so out front we're going to have negative 12 pi. And then if you want, you can change back to the shorthand notation, cosine to the 3rd of sine to the 3rd pi x multiplied by sine of sine to the 3rd pi x multiplied by sine squared pi x times cosine pi x. And that is our derivative. Let's take a look at another. Here we have y equals x squared plus 1 minus 3x to the 4th, all to the 3rd power. And you're asked to find y prime. So again, this is going to be a series of compositions. I want you to go slowly, just like we did in the last problem. Use the d by dx notation to help you along, and find the derivative here. Find y prime. So please pause the video and work on that. So the first thing we notice here is that we have all of this taken to the 3rd power. So for the derivative, that 3 comes down in front, we have all of that to the 2nd power, and now we need the derivative of what's inside the brackets. So taking this derivative here, the derivative of x squared is 2x, and here we're going to use the chain rule. We have 4 times 1 minus 3x to the 3rd power multiplied by the derivative of 1 minus 3x. And that derivative is a negative 3. So we have a negative 3 multiplied by the 4 here. That makes a negative 12. And we're here. This is our derivative. Let's take a look at another. Here we have a quotient as an inside function. So we're going to have the quotient rule within the chain rule. So what we have is something to the third power, so we're going to start with the chain rule. So for the derivative, we're going to have 3 of that to the second power multiplied by the derivative of that inside function. So now to take this derivative, we need to use the quotient rule. Bottom times derivative of the top minus top times derivative of the bottom over bottom squared. Then we should just simplify this numerator here. So we'll distribute the 2. We have 2x minus 2. And then distribute the negative sign here, minus 2x minus 2. And so that simplifies to a negative 4 up on top. And now we can just combine this to one fraction. Here we have 3 times negative 4, that's going to be a negative 12. And we have 2x plus 2 quantity squared. Here in the denominator we have x minus 1 quantity squared. And here we have x minus 1 quantity squared, so we have x minus 1 to the 4th power. And that is our simplified answer. Let's take a look at another. Where does f of x equal cosine square pi x have a horizontal tangent line? So remember, if they're asking for a horizontal tangent line, they're asking where f prime of x is equal to 0. So we need to find f prime and set it equal to 0. So to find f prime, the first thing I'm going to do is rewrite the original function without that shorthand notation, so it makes the composition a little bit more obvious to me. Now I see that this is cosine pi x to the second power, and I realize to take the derivative, the 2 has to come down. We have cosine pi x to the first power, multiplied by the derivative of cosine pi x. The derivative of cosine pi x is negative sine of pi x multiplied by the derivative of pi x, which is pi. So here we're going to have a negative 2 pi out in front, cosine pi x, sine pi x as our derivative, and this we need to set equal to 0 and solve for x. So notice that we have a product set equal to 0. That means one of the factors needs to be equal to 0. We know that negative 2 pi is never equal to 0, so either cosine pi x is equal to 0 or sine pi x is equal to 0. Those are our two cases here. Well, where is cosine pi x equal to 0? We know the cosine function is equal to 0 at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, all of the odd multiples of pi over 2. So our angle here is pi x, so pi x must be an odd multiple of pi over 2. Remember, the set z is the set of integers here. And this is how we denote the odd numbers, 2k plus 1 for k and z. So we're saying that our angle pi x must be an odd multiple of pi over 2. Well, we could divide by pi on both sides, and that says x must be an odd number over 2. And for sine pi x to equal 0, we know that the sine function is equal to 0 at all the integer multiples of pi. So our angle pi x must be an integer multiple of pi, which says that x must be an integer. So our solution looks like this. It's x equals 2k plus 1 over 2 for k and z, and x equals k for k and z. That's the solution set. But let's have an idea of what this looks like. We're asked where this function has a horizontal tangent line. Cosine square of pi x. So let's graph cosine square of pi x. And where does it have a horizontal tangent line? At every maximum and minimum we have here. And so notice that all of the blue points are where we have an odd number divided by 2. So a 1/2, 3/2, 5/2, negative 1/2, negative 3/2, negative 5/2. That's all of these blue points here. And the red points are all the integer values of x. 0, 1, 2, 3, negative 1, negative 2, negative 3, etc. And so those are all of our solution points for where this function has a horizontal tangent line. Let's take a look at another. If y is equal to 3 sine square of g of x, with g of 1 equals pi over 6 and g prime of 1 equal to 2, find y prime of 1. So they're telling us we have this composition here, but they're not giving us the inside function. They're just giving us some information about the inside function evaluated at x equals 1. So they want us to find y prime of 1. Well, first let's find y prime. So I'm first going to rewrite y by getting it out of the shorthand notation and writing it as 3 times sine of g of x quantity squared. To take the derivative, the 2 is going to come down in front, multiply by the 3. We're going to have 3 times 2 sine of g of x to the first power multiplied by the derivative of sine of g of x. And that derivative is going to be cosine of g of x times g prime of x. So evaluating at x equals 1, we're going to plug a 1 in for each of the x's, and we're going to have 6 sine of g of 1 times cosine of g of 1 times g prime of 1. We know that g of 1 is pi over 6, and g prime of 1 is 2. So that leaves us here. 6 sine of pi over 6, cosine pi over 6 times 2. Sine of pi over 6 is 1/2, cosine of pi over 6 is radical 3 over 2. So we're here. We have a 4 in the denominator that cancels with the 12, leaving a 3 in the numerator, and we have 3 radical 3. And so that's y prime of 1. So as you can see, when we need to use the chain rule multiple times for the same problem, or the chain rule combined with the product rule, or chain rule combined with the quotient rule, things can get kind of confusing. So I encourage you in that case to use the d by dx notation. So here we had to use the chain rule a couple of times, so each time I need the derivative of the inside function, I'm first going to write down d by dx of the inside function. And then I'm going to compute that derivative, and still if I need to take another derivative, write d by dx of the inside function. This notation really helps keep everything straight when you're using the chain rule multiple times, or chain with product, or chain with quotient, or when you're combining your derivative rules. So I encourage you to use that notation. And with that, we'll conclude our lesson on the chain rule.